Welcome to the last seminar of the winter term. My name is Miguel Figliosi. I'm a faculty member of civil engineering, and today we are very glad to have again Professor Peter Furth from Northeastern University. He is a great speaker, great researcher, and we're going to be covering today a topic about smart signals and transit signal priorities. So I think we are all the transit people looking forward to your presentation. So thank you for coming, Peter.
All right, glad to. Okay, let's see. This will advance. Yeah, today I'm going to talk about self-organizing traffic signals. Before I get started, I want to introduce two Northeastern students who are here. This is thrilling for me to see. So, recent Northeastern alums. Farah Naz is just graduated from the master's program at Northeastern in engineering and has moved to Corvallis. And Dylan Johnstone is also a recent, not quite so recent graduate who moved to Portland and may soon be a student here at Portland State. Okay, I'm going to talk today about self-organizing traffic signals. I'm not the first person to think of, could we make traffic signals self-organizing? So I want to give credit to some other people who kind of went before and planted this idea in my head. But they weren't transportation engineers, so they kept things sort of, at modeling, leaving out a lot of the details that make traffic difficult and interesting. The traffic signals that we know, and all of us know, they go green, yellow, red. Essentially, you can divide them into two groups. There are those that are coordinated with other traffic signals, so they can be synchronized, so you can have green waves. And then there are those that are isolated and just operate on their own. In cities in America, we have many, many more of the former, because we have so many traffic lights. They're pretty close to each other. So we tend to have lots and lots of coordinated signals. And sometimes in cities we have the free, what we call the free actuated ones. And so our signals, for the most part, they are organized, but they don't organize themselves. They've all been set. And this is a concept of maybe we could take away some of that rigid framework, forcing them to be coordinated, but have some mechanisms by which they will coordinate themselves so we get the benefits of coordination without the disbenefits of the rigid coordination that we have now. So for a starter, if you are familiar with traffic signals, you'll know this very well, but many people aren't. So let me explain what I mean about the way a simple actuated intersection control works if it's isolated away from anything else. Here you have what we call the dual ring. That's the sequence in time. You'll start with phases 1 and 5 being green. And then which one will go longer? Well, with actuated control, nobody has to say. They just stay green until the queue is empty. And there's a gap, and then it ends. So maybe one cycle, 1 runs longer than 5, maybe another cycle, 5 runs longer than 1. It's very efficient because it matches the supply to demand. It keeps the light green just as long as they want. Then when 1 ends, it lets 2 start. And you see here we have, then 2 and 5 could be running at the same time because they're not in conflict with each other. You couldn't allow 1 and 2 to run at the same time. They'd crash into each other. But 2 and 5 are in parallel rings. They could run together. And then when 5 runs out, 2 and 6 will run. Now they can't end. They have to end together because the two of them are in conflict with everything on the second half of the diagram. And then when they end, we go through the same thing with 3, 4, 5, and 6. So several really nice things about actuated cycles. One is actuated control. One is they result in short cycles. They can result in really short cycles. The left turn phases, if there's no car waiting, well, then they get skipped entirely. And if the minimum green for these through phases is, say, 10 seconds, or maybe if you want to be sure you're serving pedestrians every phase, and depending on how long the pedestrians need, they could be 20 seconds. They could cycle every 40 seconds. I mean, it could be very quick. And if the pedestrian demand isn't there and it's push button when there's no pedestrian, you could cycle in 25 seconds. You get a turn, you get a turn, you get a turn. And what short cycles mean is short waits. Okay? When you come along as a pedestrian, what makes your waiting time long is a long red, and if there's a long cycle, it's a long red. You just wait a long time. If you're turning left, you're coming up on a side street, long cycles mean long waits, short cycles mean short waits. And actuated control gives us the short waits. So actuated control is really good for transit. Never mind transit priority, just plain old good for transit because we don't want our buses to have to wait a long time. So a bus comes along and let's say the light is red, but the traffic is only serving, the light is serving the traffic just as long as it needs. Once you're done, you're over, next turn, and then our bus is going to get a turn. Think of all the times that you've been waiting at a light. The light was green for somebody else, and there was no traffic on that road. I mean, does that ever happen? That happens like 1 million times a day. That happens all the time. Why? Why do they have a green when there's no traffic there? And it's because it's not actuated control. Or it could be because there's a minimum because of pedestrians that hasn't expired yet. But most of the time, it's because the coordinated control is forcing lights to stay green where actuated wouldn't. And then a reason that actuated control is really good for signal priority is because it has a built-in mechanism for compensation. Compensation means this. If I take something away from you in one cycle, I take some time away from you in one cycle, I'll give it back to you in the next. So with transit priority, we're going to interrupt the way the cycle normally operates and hold the light green for an extra long time because we've detected, oh, there's a bus coming. Or we could also, another tactic is, your light is green right now, but I detect a bus coming. Sorry, I'm just cutting you red. Wait, I'm not finished. I don't care. I'm making you red so my bus can come through. Now, either one of those, what that's going to do is it's going to mean now you're going to have a longer queue than usual because either your green got cut short or your red got made longer. And so you're going to need some extra green time the next cycle to let your cars go through. You know what? It'll happen automatically. In that way, it's kind of self-organizing. It just, because it'll hold the light green until your queue is all gone. So that makes it really good for priority because it doesn't screw up the other traffic. The other traffic gets an easy chance to recover. Here we go. But here's the drawback. At the bottom, it makes signal coordination impossible. If I have a bunch of intersections along an arterial and I let them all just run free, they'll all want to cycle at different times. The amount of time that a traffic signal will use to cycle just depends on how many phases there are, like are there left turn phases or not, and how much traffic there is. More traffic, needs more time. So let's say I got 3 intersections in a row, and one wants to cycle every 70 seconds. And then the next one, well, I need 90 seconds to cycle. I'm kind of slower. And the next one, well, I can cycle every 55. You can see that if you're driving along that street, you just are not going to get 3 green lights in a row. I mean, they're all doing different things. You lose that coordination, and so that makes it frustrating if you're going through lots of traffic lights. So our standard way of dealing with that is to do coordination with a fixed cycle length. So instead of letting each one run at each signal cycle however fast it wants, they're all required to cycle the same length. And if this guy likes 70, this guy likes 90, and this guy likes 55, well, we usually have to take the one with the larger amount because they need 90. So we force all the signals to now cycle at 90 seconds. And then we make offsets so that we can get a green wave. This diagram shows the offsets made. Time is going up and distance is going across. So as cars go from one intersection to the next, going in the northbound direction, going up, sweet, they get a nice green wave. Of course, if you look at the cars who are going southbound, some got through here, but most of them, oops, I got a red light. Now I get a green. Oops, I got a red light. Now, oops, I got a red. Oh, now, a few couple get through, but most of them, you know. This is an example where northbound got really good service and southbound got really crappy service. And you might ask, well, isn't it possible to have green waves in both directions? And the answer to that, if you take a traffic engineering class, you'll learn, is yes, if the spacing is ideal. And the spacing is almost never ideal. So coordination can give great service in one direction. But if you have a two-way street, and I think there are a few streets around here that are two-way, if you have a two-way street, what you're going to end up is either really bad for one direction or is a compromise that's, you know, sort of good for both directions. In other words, coordination doesn't really deliver on the ideal benefit as much as we'd like it to. Now, if all the streets are one way, it's a lot easier. But most cities, their streets aren't all one way. So the performance of a fixed cycle coordination definitely gives less delay for the arterial in the favored direction. Absolutely. But for the non-coordinated movements, more delay because of the longer cycle lengths. Remember I told you there's one intersection that would rather cycle at 70 seconds, another one that would rather cycle at 55. They're all now required to cycle at 90 seconds. So that means much longer red periods. And if you're coming up on a side street, you have a much longer delay. If you're a pedestrian crossing, much longer delay. And if you're a bus that isn't in the green wave, because buses that make stops, they just, even if they start in the green wave, they get out of the green wave because they're making stops. If you're a bus, it means a long delay. So it's not good for all the non-coordinated movements, which, like I said, includes the bus, even if the bus is on the main street. It's also less safe. Now, this concept that that coordinated signals are unsafe, this is not at all understood or accepted or even talked about, as far as I've ever heard in the United States. Some of you know that I teach a summer class in the Netherlands. Some of you have been with me because Portland State teaches a summer class that we coordinate together. And I learned a lot of great things in traffic engineering over there and one of the things that they all understand is that long periods of unsaturated green is unsafe. What do I mean by unsaturated? When a light turns green, usually there's a saturated period in which the traffic discharges. Now that's very safe because who's going to walk right into the middle of, you know, one car after another? But once that bunch of cars is gone, if the light stays green for another 20 seconds, what happens during those 20 seconds? First of all, if a car does arrive during those 20 seconds, what do they see in front of them? A lot of empty pavement. And a green light in the distance that they know is not going to be staying green forever, but they don't know how long. So they want to gun it to get through. And then at the same time, what are the pedestrians doing? They're thinking, why am I waiting? I'm going to start to cross. People who have to make left turns, they think, oh, this is a good time to make a left turn. If there are crashes at intersections, it's very hard to get data to study this. If you can figure out a way, we need to do a study. If there are crashes at intersections, signalized intersections, I bet you most of them are taking place during the unsaturated green period. Actuated signals have very little unsaturated green because the way their logic is set up is you discharge your cue, that's the end of your green. Next phase is turn. But the way coordinated signals are set up, is, wait, there's a certain green band that we have to provide for two-way coordination. And so maybe you're only expected to have a bunch of cars coming through during a 10 or 15 second period, but the light's going to stay green for another 35 seconds. So they're less safe, and they lack compensation mechanisms that greatly limits the application of signal priority. And I'll explain that more as we go along. Besides fixed time control and actuated control, there's a third type of control, adaptive control. And I understand Portland now has some adaptive control on Powell Boulevard. And most adaptive control methods, you know, they have detectors out there so they can adjust according to whether the traffic is heavy or not. But they still use standard fixed cycle logic. They're using data to decide, should I change the cycle length? They might change it. You know, it might have been 90 seconds and 5 minutes ago, and now they've decided to change it to 86 seconds. And 5 minutes later, they might change it to 82. And that's nice. But still, they change the whole street to that same cycle length. They run. They have standard offsets. It's still all the disbenefits of fixed cycle coordination are there. The benefit that they add is at least the fixed cycle length that they're using is well adapted to the traffic demand. There's a fourth kind of control that has been studied, but it's just not used in practice, where they're actually doing optimizing, where they know about traffic that's coming from everywhere, and they are just everything is free. Should I change the cycle? Should I change the light now? 2 seconds from now, 4 seconds from now, 8 seconds from now. So these things they've been studied in the literature, they've been tested, but the computational burden is really high. And even if we could get over that, because of course our computer power is getting better, they have an inherent problem, which is you can't predict the traffic 30 seconds out. And that's what you need, 30 to 60 seconds out, because the traffic you're going to get is traffic that's coming from other signals, and they're going to be deciding what to do. So instead, the direction of improvement that my research is taking is saying, let's start with basic actuated control. You know, it's really nice. It has so many nice features. It just has this one weakness. It doesn't provide coordination. So let's see if we can add some coordination mechanisms so that without imposing coordination, things will coordinate and I'll get better service on the arterial. And I start out by recognizing that, you know, actuated control already has some what we call self-organizing mechanisms. One, it'll find the best cycle length. It does the compensation that I talked about. But the third one, this is a cool one, is that it will hold the green once a platoon has arrived, and that will get two things in control. Let me illustrate. Let's say here's intersection 1 that wants to cycle at 90 seconds. That's just what I like to do. And here's intersection 2 that likes to cycle at 75 seconds. Maybe they don't have some left turn phases, so I like to go around faster. Okay, now let's say at a certain point in time, the two are just in sync. So cars released from intersection 1, when they arrive at intersection 2, the light turns green just before they arrive, and they sail right through, and it's great. It's perfect. Now what's going to happen the next cycle? Well, it's going to take me about 90 seconds to get back around to releasing my platoon. It's only taking the other guy 75 seconds later, he's ready, he's turned the light green, and my platoon hasn't arrived yet. Now, there's a minimum green. And there might be a couple of cars that turn in from the left turn. So, if we're lucky, my platoon will arrive before that green ends. Right? Like, suppose the minimum green was 20 seconds. Then it'll work. My platoon will arrive. And once my platoon gets there, the logic of actuated control is you just hold the green. So the green, because you're waiting for a gap, and while my platoon is coming through, you ain't going to see no gap. So my platoon goes through, And then finally it ends, so we stayed coordinated, and that will keep going on. But when I say the one likes to cycle around at 90 and the other one likes to cycle around at 75, those aren't fixed numbers, of course. Maybe one cycle, because there was more people turning left or whatever, it didn't take me 90 seconds to go around, it took me 100. And let's say, meanwhile, my next signal, instead of taking 75, they had less traffic than usual. They cycled around in 60. Now, there's no way that my platoon, when they arrive, is going to meet a green light. So, and then it's also think about the other direction. See, it worked going from the longer cycle intersection to the shorter cycle one. If you think about, well, how about going for the platoon going from the shorter cycle one to the longer cycle one? Nope, there isn't a mechanism there for getting them. So some mechanisms are already there, but we need more mechanisms for coordination. So what my research has done is propose one main mechanism for intersections that aren't really closely spaced, and then a bunch of other things when they are closely. I'll get to that. But I'm going to skip over this part and go right to the main coordination mechanism, and that is something that I call a secondary extension. So the question is this. Here we are, the light for the traffic heading eastbound. It's green, and here are the last two cars that went through, and now there's a gap, big gap. So I'm ready to gap out. Okay? Gap out means, because I detected a gap, I'm ending the green. But at that moment, I look upstream and I say, is there a platoon coming? If there is, maybe I will hold the light green. That's the secondary extension. Should I? And I think everybody would agree that the conditions for whether to hold should be based on, number one, is there excess capacity at this intersection? Because while I'm holding that green, holding the light green, I am wasting green time, right? The light is being held green and nobody's using it. Can we afford to waste green time? The answer is most of the time, yes. We have excess capacity at most of our signals most of the time. So, but sometimes not. So if I'm oversaturated or on the verge of oversaturated, I will not spend my capacity in order to get coordination. Capacity is more important. Because if I go over capacity, now people are waiting 2 cycles, 3 cycles, queues start getting long, it all falls apart. So that's the first condition. Is there excess capacity? And second, tell me about this platoon that's arriving. If the platoon only has 1 car, 2 cars, that ain't much of a platoon. So for me to hold for a platoon, what I want that platoon to be is 3 things. I want it to be dense, I want it to be large, and I want it to be very close, imminent. The closer it is, well, the less green time I'm wasting, waiting till it gets there. The larger it is, maybe I waste some green time, but once it arrives, I'm wasting that time to serve lots of cars that if I didn't serve now, I'd have to serve in the next cycle. And the denser they are, then I'm not wasting time while the platoon is going through. So operationalizing that as a measure of how qualified a platoon is for a green extension is how much lost time will there be per vehicle in the coming platoon. And the lost time is the difference between how much time am I going to hold the light green minus how much time am I going to use. And used time, you just have to understand the concept that when traffic is passing through a stop line, the saturation headway, the closest, the smallest average headway that they can go through is called the saturation headway. It's about 2 seconds. So if I'm serving 10 cars, well, 20 seconds while I'm serving them, that's completely used. That's not wasted. I would have needed, to get them through any time, I would have needed to spend 20 seconds. So ask, how long am I going to be holding the green? And now subtract how much of that is going to be used. So let's say if I hold the light for 30 seconds, 10 cars can get through. Then I'd say 30 minus 10 times 2. So that's 10 seconds is wasted. And then divide that by the number of cars. 10 seconds wasted for 10 cars. I'm wasting 1 second per car. So that's our measure. And if you think about that measure, if you take a base condition and say, well, what if the platoon is closer, is more imminent? You'll see that measure gets better. What if the platoon is larger? That measure gets better. What if the platoon is denser? That measure gets better. So that measure takes care of all those things. And then the other condition was, well, what about capacity? So the limit is this. On the bottom axis is volume to capacity ratio for the intersection as a whole. Once that V over C ratio gets to 1, we aren't giving any secondary extensions. Nobody's qualified. As the V over C ratio gets smaller, I'm willing to accept more and more lost time per vehicle up to a limit of 2 seconds. So if we're, like a lot of intersections are operating around 0.7, that means if it's going to be 1 second lost time per vehicle, nope, you just don't quite qualify. But if you are down to 0.8 seconds per vehicle, then that's a platoon I'll wait for. Okay, so that's the idea. If you ask, how do you know those are the right parameters? I did some kind of back-of-the-envelope calculations to come up with what seemed reasonable, and then we did some sensitivity testing. You know, what if we change the maximum? What if we change the cutoff point? What if we change the slope? And the results hardly made a difference. They got better in some cases, worse in other cases. So we were happy with this. And then, and also I put in the rule, only 1 secondary extension per cycle. So remember, the secondary extension, it starts when there's a point that there's a gap. You're ready to gap out. Shall I extend? Oh, okay, let's extend. Now, once you've extended, when does the extension end? It ends when you gap out. You hold for your extension time, and then you can hold longer than that as long as there's cars coming through. But once you gap out, you don't ask, how about another secondary? No more secondary extensions. The other traffic needs a turn. So we tested this within the traffic simulation VISM. Any of you use VISM in your research? Look at all those hands. Fantastic. So I know some of the writing here is small, but here we are at time 368.8. And this intersection here, you see there's a bunch of cars that have just passed through. And here there's one that's about to pass through. My extension detector is up here. That extension detector has said, you know what, I have been unoccupied for about 3 seconds, and that's enough for me to say, gap out, time to end the green. So at that point, I now look upstream and I say, is there, who's arriving? Is there a platoon that's arriving? And I've got detectors, and I'm using the detectors up here to count cars. I've been counting how many people have been going across and when they're going across. And from those counts, I have a profile that I update every second of what in each, over the next 20-second horizon, when do I expect cars to be coming? So I've got a prediction. I got a car coming, 19 seconds from now. There's another one 14 seconds from now. There's another one 13. So from that profile, I make the calculation of that lost time per vehicle. Oh, and I forgot to say, in that calculation, you say how much is the extension and so on. How do you know which extension to use? We do that for. We say, what if there's a 2-second extension? 4 seconds, 6, 8, 10, 12, 14, 16, 18, 20. And of those values, one is better than any of the others, the one that's the best, and that's the one we'll use. So we'll find out which extension gives us the best measure. That's the extension we'll make. So we look over here, and we decide, and this platoon, even though it's spread out, if the cars are moving fast, it's the time between cars that matters, not the space. So at the speed they're going, this is a pretty dense platoon. So, yep, we are going to hold. So you notice that time, 368.8. So at time 368.9, you see this little green light here. This light has turned green. If I go back a second, that light was red. Now, what is that light? This is a dummy traffic signal. You can do that in Vissim. I just kind of put a little imaginary stretch of road with a traffic light in it. It doesn't stop anybody. It's just for my eyes to see. It'll turn red and green whenever I tell the program to. So I tell the program, make that thing turn green whenever we're in the state of secondary extension. That way I can see when there's a secondary extension. So you as a driver would never see that. That's just for us as an analyst. So at time 369, now the secondary extension is on. And we're now, let's say the extension we decided to do is 18 seconds. Maybe it was 12 seconds. I don't know. I'm committed for that long. And after that point, I will continue to hold the green until we gap out. So it turns out that it doesn't get the secondary extension turns off, and it doesn't gap out until time 399. And you see all these cars, they got through. So that way, my platoon that got through one intersection can get through the next one, and I got nice coordination on the arterial. We also do secondary extension in the non-critical direction, and usually on an arterial, one direction has more traffic than the other, but we won't allow as long. So then the next thing, so that was the first mechanism, secondary extension. It seems like a pretty simple idea, but as far as I haven't seen any place in the literature where somebody has proposed that in the past. Secondly, secondly, there's a set of rules that we put in for when intersections are closely spaced. When intersections are closely spaced, you get a problem with queuing. That if the queue from one intersection can't fit because the block just isn't long enough, it's going to then spill back to the next intersection. There they do need closer coordination. Okay, so in this case, we are going to impose some rules to force them to be coordinated, but not with a fixed cycle length. The basic logic is this. In any group of closely spaced intersections, and we keep our groups small, maybe 3 intersections, one of them is critical relative to the other 2. One of them needs a longer cycle length. So the rule is this. Everybody follow the critical guy. That's it. So if the critical guy says, okay, this cycle, I need 90 seconds, we're all going to go 90 seconds. Next cycle, I need 70 seconds, we're all going to go 70 seconds. That's the basic logic we're trying to follow. So we call this dynamic coordination. This is a term that Zurich was using for their traffic control, and they were using logic like this. So they're the ones I got this idea from. I've told you within a zone the critical intersection is the leader, but the cycle length is not predetermined. And the control tactics, what we care about is protecting the critical intersection from starvation and spillback. Those are 2 things that will waste capacity and waste green time. But at the non-critical intersections, they can afford to have a little bit of starvation and spillback, as you can see. So here's an example of dynamic coordination. These examples are from Beacon Street in Brookline, Mass, where there's a light rail running right down the middle, and my home was only 2 blocks away from there. But I always tell my students, in your projects, make the traffic work better for your professor. You'll get a good grade. So here we have a situation where this is the critical intersection, and this one is coupled with it. They're in the same zone. And the critical one is not ready to turn green yet. The pedestrians are still crossing going north-south. And we know, because pedestrians, there's a countdown, we know that this one is not going to be ready to turn green for maybe 10 seconds. So we're ready to turn this one green, but what's the use? The cars are just going to join the queue at the red light. They aren't going to get anywhere. So instead, what we're going to do is say to the non-critical one, you just wait, and we're going to keep the light green on the side street, because who knows, maybe another car will come along that will be able to enjoy it. So you see the dummy signal here. The side street is just getting an extended green. Maybe this car is going to make it through. While we wait to see, wait for our leader. Once the leader turns green, then, once we know when the leader turns green, we do a calculation of when our upstream one should turn green, so they can just match it, and it works very well. Okay, I'll skip over that. When the intersection, if the intersection becomes oversaturated or close to oversaturated, then capacity is more important than coordination. I said that before. Throughput is the most important thing. Because once you're over capacity, number one, coordination is meaningless. If you're waiting 2 or 3 times at a cycle, who cares? You get a green wave to the next one, and then you wait 2 or 3 times or something like that. So we have some rules for that. One is we use a spillback detector. Now that's actually a pretty common thing in arterial control today. That if we see that, okay, the queue is building up, once there are cars sitting on top of these spillback detectors, then that will tell us, turn this light red. Number one, I don't want things to spill back. And number two, I don't want to waste green time, because the light's going to be green, but nobody's going to be able to move. Switch it, serve the cross street, get some of them out of the way, so use my time better. So, and then I can also use that to inhibit the start of green. If I'm ready to start green here, but the spillback detector is occupied, well, I won't start the green. I'll let the cross street have more green time and hope to serve some cars that way. And the next thing is, if I want to protect the critical intersection, here's the critical one, then I will allow a little bit of starvation and a little bit of spillback at the non-critical one. So, for example here, if the way this light is green, after these 6 cars go through, there's going to be starvation, right? The light's going to be green, but there's no traffic feeding it, because at the critical intersection, the light is red. I would not let that happen at the critical intersection, but I will let that happen at a non-critical one, because the non-critical one has excess capacity. And I'm going to tell this guy, just keep holding your light green and wait for the critical intersections so that traffic can go through. All right, enough on that. Here's an example from our simulation. Our time, 4989.6. This is my critical intersection. And if I turn the light green there, I'm going to have starvation at the critical intersection, because, look, there's such a small queue, and all these cars are stuck up here. Well, I don't want starvation at my critical intersection, so I'll turn the light green at the non-critical one, and suppose now they get stuck. That's okay. And suppose it spills back through the intersection. That's okay. That spillback will only last 15 or 20 seconds. It'll just be while the light is green. So it won't inhibit any cross-street or pedestrians, because there's no cross-street or pedestrians going at that time. Then this one will turn green, and then the whole platoon will clear out. Okay, so the platoon has arrived. They are spilling back a little bit in here, but it's okay. Now it's become one solid platoon that will just move right through. Okay, then there's another tactic here, and I'll skip that because of shortage of time. So now let me tell you about some tests that we did. One was a test looking at oversaturated situations, an oversaturated situation. This was a test that had been done by a researcher named Lieberman. He developed a really complicated method with all kinds of optimization that he called impost, that was specifically designed to make traffic work better in oversaturated situations. And what he reported in his paper was actually enough that we could replicate that situation and then test our method in exactly the same environment. And in the test, there's a 30-minute period in which this is the volume capacity ratio. Volume capacity ratio is at 128%. So we're way over capacity. Leading up to it, traffic gradually decreases, and then afterwards, traffic goes down. When we look at the 5 methods, here's our new self-organizing method. This was Lieberman's impost method. And then Passer, Transit, and Synchro, those are 3 softwares often used to get signal timing settings for coordination. During the low traffic periods, they're all good. During the overcapacity period, our method and impost are way better than the other. But afterwards, our method is much, much better, because what our method did was it focused on throughput. And so all the residual queues, you can't avoid having residual queues when there's overcapacity, but we got them through. We wasted the least amount of green time, so we got them through, and now we're down to very low delay, and in the next period, very low delay, so that when you average out, our method and impost are much, much better than the standard methods that don't account for that, and ours was still a little bit better. And so we did this section, did a simulation on a section of Beacon Street with 12 signals with highly variable spacing, lots of pedestrian activity. So don't trust anybody who does a traffic simulation of signal priority that left out pedestrians. If there's no pedestrians, there's probably no transit. There's no point in giving transit priority in a place where there's no pedestrians. So, and pedestrians really constrain traffic signals, so you need to account for them. So this is the volume profile that we used. It rises to near capacity, but not quite, because that's the real situation. Transit's running every 7 minutes. When we applied conditional priority, we gave priority if the headway was greater than 315 seconds. So if the headway is less than 315 seconds, that means you're just too close to your leader. I don't want to give you priority. I want you to get pushed back because I want to keep the spacing closer to 420 seconds. And we used green extension and early green. So here are our results. So first, forget about TSP. Let's just look at the no TSP. Apart from transit, how well does the self-organizing method work? Well, we lowered average network delay from 68 seconds to 58. So a nice improvement, 14% improvement. And the main difference, like I said, is that with actuator coordinator, it's a fixed cycle. Everything's cycling at 80 seconds. With self-organizing, every signal can do whatever it wants, and on average, they were cycling at 69 seconds. So that means lower pedestrian delay. That means better safety. Then when we put transit signal priority in, the network delay for cars, it goes up somewhat. This is this is with the standard method with coordination. And the delay for the train drops to 13.7 seconds. So there's 6 seconds per intersection improvement. That's not bad. But with self-organizing, instead of 13.7 seconds, we're able to drop that delay to 7.1 seconds, because we can give more aggressive priority, and because the system heals itself, and and the cycles are shorter, so we get much better result there. Another thing to look at is headway regularity. On this particular line, once a train is late, there are more people waiting for it. And then it gets later and later and later, and we get some really bad crowding. So they arrive at the beginning of the section already. This is the coefficient of variation of headway. So that's our measure of irregularity. If everything were perfectly on schedule, that would be 0. So they arrive around 0.37, And the normal way, without any priority, the irregularity gets worse and worse and worse, reaching 0.5. And at this last stop, St. Mary's, I mean, it's really common for there to be people on the platform, and they just can't get on. Because once a train is late, it's just becomes so full. With our self-organizing signals with priority, you see how it's hardly any different at St. Mary's than it was at the beginning. Because we're able to give priority to the early trains, priority to the long headways, no priority if the headway is really short, and there just aren't these long delays. The irregularity happens because one train gets a long delay, another gets a short delay. We keep everybody's delay short. We lowered the average delay from 20 seconds to 7 seconds. So much better. So we still have more to do with using this as a base with really aggressive priority. When I say really aggressive, I mean things like, how about a 25-second or even a 30-second green extension? How about phase rotation? How about predicting when the bus is coming and holding the light even when there's a near-side stop because you've predicted that I think the bus will be ready to go. So we're going to still experimenting with that. But for now, my conclusion is that the self-organizing logic, it delivers the benefit of coordination that we wanted, while preserving enough of the benefits of simple actuated control that we get overall better performance. It's better performance just for cars. Now, it's not better for the cars that are just driving straight down the arterial. But if we average in all the cars, so not only the ones who are going down the arterial, but the ones going in the other direction, cross-street turning, if we average all the cars, they're actually better off with self-organizing because it gives that lower cycle length, and it still gives enough coordination. That the coordination mechanisms that we added, I wasn't sure. Do we have to add more mechanisms? No, this seems to be enough. The secondary extension, and then the special rules for the coupled intersections when it's close. And then the last thing, which I really like, the self-organizing logic, is inherently flexible. It's got shorter cycles, which is better for transit in the first place. But it's self-healing. So that if you do interrupt things for priority, you just screw up the coordination for priority, it doesn't have a rigid coordination. It just naturally, things just naturally come back into synchronization. Okay, I showed you the intersections that are cycling. One is cycling and its neighbor, shall we dance together? Yeah, okay, so we'll link arms. But maybe the next cycle, you know what? Let's uncouple. I'm going to dance with this one. And, so a bus comes along and I say, we got to let go, man, because it's going to take me a long time to cycle. You just keep moving. But the mechanisms are there for us to just come back into coordination again without a lot of capacity loss or interruptions. So I think it's a very promising way to go. I've often said that with people who study in the field of intelligent traffic signals, I think they don't give enough attention to intelligent traffic transportation systems, ITS. They don't give enough attention to traffic signals, which have been using intelligent logic for a long time, and which control traffic, all over the place. And so by putting this kind of intelligent logic in, we can get better performance and all the directions that we want to move, better service for pedestrians, better service for transit, safer in terms of having less of that unsaturated green period. And it's probably better for bikes, too, but I haven't studied that. So I think it's a good way to go. So now I'm glad to take any questions that you have. So, yes, sir.
Does the delay that's being used to calculate the secondary extension take into account the number of pedestrians waiting? Is it just vehicle delay solely, or can you count pedestrians to say, well, this pedestrian is going to have to wait an extra 20 seconds?
So let me just clarify. I'm not calculating what delay is going to be imposed on others. I'm not calculating that at all. What I'm calculating is how much green time am I going to waste? Now, in general, if you waste green time, you're hurting somebody. But I'm not counting how many somebodies are hurting, whether it's people in cars or pedestrians waiting. So the general idea is that I like short cycles. I want things to move around fast, because then all the people who are waiting, pedestrians and in cars, will get served sooner. So I'm not going to make anybody wait unless a lot of people are going to benefit from it. So I'm calculating that's the calculation. Okay, yes.
My question was, you said it's safer to have less unsaturated traffic green times.
Right.
But when you have a secondary extension, doesn't that make the unsaturated green longer? So doesn't that become...
So when there's a secondary extension, there is a period of unsaturated green while I'm waiting for that platoon to arrive. Once the platoon gets there, now it's saturated again. So, yes. I mean, if I don't want to have any unsaturated green, well, then I can't have coordination. So we will have some, but nothing like what you get. I mean, I don't know about the streets right here by Portland State, but I could tell you about the streets right by Northeastern University. I mean, you stand there any time of day, and when the light turns green for Huntington Avenue, the cars vanish after, how it might take 8 seconds, might take 16 seconds, and once they're gone, the light stays green for 30 or 40 seconds while there's no traffic. So we don't have any of that going on. Yeah.
If you were to bring this into the field,
Yeah.
what sort of infrastructure needs would you need?
That's
Do
a
you
good
use
question.
existing controllers? Do you need common infrastructure, et cetera?
That's a good question. All right. So number one, we need more detectors, because we're counting cars. You're not supposed to do that in Las Vegas. But it's okay on our streets to count cars. So we can make double use of some detectors. The same detector that's used for gap out, I can use them to count cars. But sometimes I need some extra detectors to count cars. And then, of course, every detector has to be connected. But there's nothing special there. The special thing is that the logic that changes the lights, where does that come from now? The way things work in the industry, the companies that make and sell traffic signals, they are not only hardware companies, they're software companies. They write the software that runs the traffic signals. And they've written software for doing all the standard stuff we do. You want to do something non-standard, somebody's got to write the software. So there are two ways that can be done. One is you get a supplier, you tell them, I want this logic. Do you think you can program this for us? And they might say, yes. They might charge you for it, or they might say, if you're buying enough traffic signals, it's okay, we won't charge you for it, and we'll offer it to other customers. Or you get a third party, because there is a communication protocol for the interface between the hardware and the software. Anybody's software should work with anybody's hardware. So I can buy my controller equipment from company A, while company B provides software, and there's a standard interface, so when I want to say turn the light green, I connect to the hardware and say make that light go green. So, I often say we were able to put a man on the moon. We should be able to get the light green when a bus is coming. So those, you can't do it in a routine way. It would need some deliberate action and expenditure, but it's not insurmountable. Yeah.
Practically in the field, if you have a secondary extension with a transit bus going through, how would the operator know that the light is being held?
Oh, actually, they don't. I mean, the operator, what?
So that brings part two, is that if the operator doesn't know the light is being held for them, and they see this long green, doesn't that then create an unsafe situation where an operator is having to determine whether or not to accelerate through an intersection or to stop because they don't know how the signal is going to behave because of the secondary extension?
No. That's what yellow lights are for. Okay, so the way you're supposed to drive, you as a driver and the bus drivers, is when the light is green, go, and don't accelerate. Just go at the normal safe speed. When you see the light turn yellow, that's a time for you to decide based on my proximity to the signal. Can I stop safely? If I can, I will. If not, I won't. So when the light is green, yeah, you don't know whether it's in green extension for a bus or secondary extension. You don't know. You just go until the light turns yellow, and then when it turns yellow, you stop. That's the way it is at every traffic light. I mean, even if there is no extension, when you're approaching a light, the light is green. Do you know when it's going to end? No, nobody knows when it's going to end. We don't have countdown signals for when the light is going to end. By the way, in some countries they do. My students from China and Iran both tell me that they have countdown signals, so you know when the light is going to, when the green is going to end. Does that generate speeding? I don't know. I didn't ask them. But okay, I think I've answered that. Satisfied? I've been told you guys have to ask questions. So, come on. There's got to be some more good ones. Hi.
Hi, Peter. How's it going?
Great. Great to see you.
I have a question. I can see how this would be valuable in a place like Boston because I've seen your grid.
Yeah.
But here in Portland, especially in downtown, we have, a lot of one-way streets. We have a tight 60-second cycle.
Yeah.
How would this be beneficial to?
Yeah, I'm not so sure it would be very beneficial in a tight downtown grid. I mean, you have this kind of ideal spacing that allows for short cycles and where things are coordinated well. So I think it would work, and what it would do is it would just probably reproduce the same 60-second cycle. Actually, it would make a shorter cycle. On your streets, I see so much unsaturated green. I see so many times the traffic is all gone. Why don't we switch? But I understand from Peter Kuntz that it's mostly because the streetcars, they're so long. It takes them a long time to get through, and when they've tried shorter cycles, the streetcars often were not getting through. So that's why they were lengthened from, I think they were 42 in the off-peak. And then now they had to lengthen them to 56. But, there are a lot of cities where it's 120. You'll never find a 56 in Boston. I mean, I send my students scouring. I say, anybody, find me an intersection that cycles in less than 60 seconds. I want to know about it. They're that rare. So, yeah, in tight, and the other thing about downtowns is that there are pedestrians all the time. So you have to build them in. You got the minimum green for the pedestrians. So this is more outside the tight downtown grid. Yeah.
Just to play devil's advocate, it seems like you're increasing capacity, which is a good thing, and you're decreasing delay for pedestrians, which is also good. But could you possibly be inducing demand for car drivers by increasing that capacity without widening the road?
Yeah, that's always a possibility. Now, where you say I'm increasing capacity, the only place I'm doing that is when it's oversaturated. I'm helping to make the oversaturation dissipate faster. Yeah, that's always a possibility. I mean, we could just, put roadblocks in the road, just, put barricades everywhere, and that would reduce demand. But when there's congestion and big delays and it spills back, it generally hurts everybody. Unless transit is in its own dedicated right-of-way, those queues are going to be delaying buses and streetcars that are going to mix traffic. It's riding a bike through streets where there's congestion is no good for anybody. On busier roads, periods of congestion is when the accident rates go up. So I think it's all right. Yes, Miguel.
People watching online, one question was in terms of transit priority and providing extension versus a bus in the other direction coming and requesting extension. I mean, requesting, early green. And the other question was, you have two buses from different directions approaching in terms of providing priority for the priority.
Yeah.
How would your logic work?
All right, so this question has come up over many years, with transit priority, people say, well, what if you have two buses? I want to give a preliminary, very strong answer, which is, if you let that stop you from giving priority to one or the other, you're doing the wrong thing. I mean, so, you know, and that's what, like, the first thing is just give priority to one of the buses. If you're giving, you know, our problem is not that we're giving priority to the wrong bus. Our problem is we're not giving priority to any bus. Or our priority is so timid that we're just, you know, priority in one cycle, so no priority in the next. The problem now, to really answer the question, the problem with how to decide which bus to give priority to is how long in advance are you getting these priority requests? Most of the time, we're getting the priority requests about 15 seconds in advance. I mean, you just don't have a lot of time. So if there are two buses, that means one bus came along, and then, you know, in 15 seconds, that bus is gone. That bus is served. So 5 seconds later, another bus comes and says, oh, give me priority. That, number one, it's not going to happen very often. And number two, there's just not that much you can do. You know, so you could say something like, oh, yeah, let's cancel out the first one because the second one is more important. But what if the second one arrives 13 seconds later? Now, in 2 more seconds, your first bus is going to be served. I mean, you see what I mean? So there are, I really like the idea of predictive priority, where you're getting your priority requests 2 minutes in advance. And now, during those 2 minutes, you are massaging cycle lengths, making cycle lengths shorter and longer as need be, so that when the bus arrives, it's going to arrive in the middle of a green, and you're not going to have to, quote unquote, give priority. Now, in that case, in a 2-second window, there I might get several competing requests, and there I might make a decision to do something about it. So the simple answer is that in our current context, with very short prediction windows, it's moot. It's just, the question just disappears. It only really becomes something when it's a long-term prediction, and we're hardly doing that at all. But if somebody wants to work on that as a research topic, that's a really good topic.
The question was, like, when you're deciding to extend the grid in one direction,
yeah,
there is a bus that starts to request priority at the same time. How would you change the...
Explain that, say that again.
So, like, if you show that graph in terms of when, depending on how many seconds per vehicle,
yeah,
decision loading,
right,
how that graph would be, you know, modified when you have priority in terms of you totally disregard that graph and just give priority to a bus in another bus.
Yeah.
Okay.
Okay, so the secondary extension rule, that's just subservient to bus priority. So if I get a bus priority request on a cross street, well, that takes precedence. Boom. But that makes me think that, you know, we could change that calculation, lost time per vehicle. We can make that lost time per person. So what if there's a bus that's part of that platoon? All of a sudden, that platoon's value should go up. And that way, we could actually combine secondary extension with priority. Is that what you were about to ask? What a brilliant idea. Okay, how about time for one last question? We won't go until somebody asks one. No. Yes,
So, when Professor was saying that if we have buses in 2 different approaches who are asking for priority, when we write the phase rotation logic,
yeah,
so if we can predict a bus, let's say, quite upstream, then if we can rotate the phase, that actually in one time in my model that actually gave priority to both of the buses.
So one of them was approaching in which direction?
One of them was approaching to take a left turn.
Let's say eastbound left, and the other?
And other one was going westbound.
Westbound through. So maybe if no priority action was taken, they would have both arrived at the same time, and one would have had to wait for the other. But instead, she's able to do something so that one got served and the other one got served very soon afterwards, something like that. Very good. Okay, thanks all for paying attention.